So let's look at the PYQ radar first. In this, we will be identifying and explaining the issues while communicating and accessing the data in the wireless medium, right? And we'll also discuss about what are the survey routing protocols which are used by the routers. Then we'll sketch the extension of Arduino, what are the components of Arduino in detail, and we'll also talk about the wireless sensing network. These two are the questions from unit 2, I guess, wireless sensing network and components, and also the node behavior in wireless sensing network. We'll talk about IDE as well, what is that, and various sensor deployment strategies. And one of the main topic is the MAC protocols as well. So we'll discuss those in unit 3. So let's get to it. What is basically wireless access medium? Wireless space is a shared resource. When an IoT device transmits the data, it sends out the radio waves through open air. This open air is what we call wireless access medium. So it is a shared physical space, right, through which devices transmit the data. Because multiple devices must share limited frequency band, a medium access control layer is necessary to coordinate the transmission and prevent coordination. So if two devices in the same area try to transmit the data on the exact same frequency at the exact same millisecond, their radio waves physically clash. This is called collision. So when the collision occurs, the data is completely scrambled and corrupted. So to prevent this, we rely on MAC layer, medium access control layer. So think of a MAC layer as a traffic cop or a meeting moderator whose sole job is to coordinate the transmission so that the devices can share the airways without running into each other. So what are the major bottlenecks? What are the issues that occur while transmitting the data? Very first is collision and interference. As we just said, overlapping waves equal dead data. So the device has to waste time and power transmitting the message, right? So that is why it is a major issue. Second is scalability. If you have 5 devices sharing a router, collision are rare. But IoT network frequently involve thousands of sensor nodes packed into a single smart factory or a farm. So as device density scales up, the mathematical probability of collision also rise, right? Then comes power consumption. For an IoT node, nothing drains a battery faster than talking. So if a node is forced to constantly resend its data because of collision, or if it has to stay awake in an active listening state, just waiting for an opening in the airways, its battery will die in weeks instead of lasting years, right? And then we have latency. In a congested network, data gets backed up. For a routine smart home like temperature update, a 5-second delay doesn't matter. But in industrial automation or in medical heart monitor, a 5-second delay could be catastrophic, right? And then there is a hidden node problem. So you need to understand this thing. This is a classic question as well. What is the hidden node problem? So imagine a central access point. Let's call it node B, right? So node A can see node B, alright, and node C can see node B. So it is the middle one. However, node A cannot see node C because they are too far away from each other. So node A looks at the airways, hear nothing and assume this medium is free. But at the same time, node C is also sending the data, right? Because for node C also there is nothing in the medium. So they both transmit to node B simultaneously. Okay, so they both transmit simultaneously to node B, causing a massive collision at the node B. So they are completely hidden from each other, leading to unintentional data destruction. So this is known as hidden node problem. To fix these issues, we implement specific communication protocols. So the first is TDMA, called TUDMA. I call it TUDMA to remember it. So think of TDMA as a strictly structured corporate meeting. Alright, so what happens in a corporate meeting? The moderator points to each and every person and says that you have exactly 30 minutes to speak, and then it is the next person's turn. So TDMA works in the same way. It divides the wireless frequency into different time slots. Okay, so each IoT device is assigned to its own specific slot and then sends the data in that particular slots only. So pros are that it eliminates the conclusion because every device knows exactly when it is allowed to talk. So collisions are reduced to zero, and it is also incredibly energy efficient. So if a sensor is assigned to, for example, slot 5, it can completely power down its radio and sleep during the slot 1, 2, 3, 4 because it doesn't need to listen or send the data. So this saves the massive amount of battery. But there is also a con, that it demands absolute perfection in the timing. So all thousands of nodes must have their internal clocks perfectly synchronized to the microsecond as well. So if one node clock drift even slightly off, it will bleed into other node time slot, and this will cause a problem in the system. So this is the first type of protocol. Second is the CSMA, which is called as Carrier Sense Multiple Access, and CA with collision avoidance. CA stands for collision avoidance. So if TDMA is a structured meeting, then CSMA is a polite dinner conversation. It uses listen before talk approach. Okay, it uses listen before talk approach. So before an IoT node transmit, it senses the carrier wave. It listens to the air waves. If it hear another device talking, it backs off. It doesn't just wait until the other device finishes. It wait for a random back off period of the time before checking again. Why random? Because if multiple waiting devices all jump in a split second the airway cleared, they would instantly collide. That is why there is a random back off jumping period required in this. So there is pros that it is incredibly simple to implement, right? And requires zero complex time synchronization. We require time synchronization in TDMA, but it is not required in carrier sense multiple access. But it isn't perfect, right? There are cons, that if two devices listen to airway at the same microsecond, they hear silence. If I am hearing, you are hearing, we both hear silence, so we both might start talking at the next microsecond and they will still collide. So under heavy dense IoT traffic, this protocol becomes highly inefficient compared to TDMA. Now if we talk about the techniques, what are the techniques? So when the wireless medium gets heavily congested, advanced network don't treat all data equally. This is known as QoS management. So what is the function? QoS prioritize the traffic based on the urgency. Think of it like an emergency lane on a crowded highway. Why it is used? Because somebody has a very urgently need to reach the hospital. That is why that pathway is cleared, right? And so imagine a smart hospital network. So a smart thermostat sends a data packet saying the room temperature is 24 degrees Celsius, and at the same moment a wearable cardiac sensor sends the packet saying the patient heart rate is dropped to 40 bpm. So this QoS intercepts this packet at MAC layer, pushes the routine temperature update to the back of the queue, and grants the critical medical alert immediately. So high priority access to medium to ensure that there is zero latency. Okay, and then second technique is adapted modulation. which is all about changing how we encode data based on real-time environment. So it dynamically alters the data encoding scheme based on the current quality of radio signal. Think of an environmental sensor node that is deployed in a windy, rainy mountain range. When the weather is clear, the radio signal is pristine. It is clear, right? The device uses high order modulation scheme, meaning it packs massive amount of data into a single radio wave transmission to get over with quickly, right? Suddenly a massive storm hits. It causes heavy radio interference. So instead of stubbornly trying to send those complex fragile packets which would get corrupted and require constant battery draining retransmission, the node's MAC layer adaptively switches to a lower, a much robust modulation scheme. What it does, it sends data at a lower speed but uses a highly reinforced signal structure to guarantee that message safely punches through the storm interference. So it beautifully balances the speed, reliability and power consumption. Now let's closely look at the MAC layer. MAC stands for Medium Access Control. In networking stack, the MAC layer is a critical sublayer of data link layer. If you have read about operating system, there are various layers. So data link layer is the second or third layer and MAC layer is part of it. So what is MAC protocol survey? It is an evolution of how different rule manages our shared wireless space. Think of the airways as single shared highway, right? So if everyone drives onto it whenever they want on the highway without lanes or traffic light, you get an immediate multi-car pileup, right? So MAC layer act as a civil engineer department of our network. So what it does basically, it coordinates how multiple IoT devices share a common wireless communication, and it also evaluates how different protocols handle the same physical space. So it handles 4 core responsibilities. First, it helps in collision avoidance. It orchestrates signals so that they don't crash into each other on the same frequency. It also provides energy management. This is critical to IoT, right? Energy management. So the MAC layer decided when a node radio transceiver can shut down and go to sleep. So this saves the precious battery life. It also ensures scalability, maintain clear channels when you have 5,000 new sensors to the room, and it also addressing, making sure that every data packet has a precise hardware address so that it doesn't get delivered to the wrong node. So whatever problems we are facing in wireless access medium, we have answers in MAC protocols. So first type of MAC protocol is contention based protocol. Alright, so the word contention means competition. So in this protocol there is no master schedule or device simply compete for the airways. There's a competition. It is an ad hoc random access approach. Alright, so it is a random access protocol and device compete for the medium. They are flexible but can suffer from collision. So first type of contention based protocol is Aloha. So we'll talk about pure Aloha and slotted. Okay, ALOHA, I call it Aloha. So first is pure Aloha. This is developed in Hawaii in early 1970s. Alright, so this is the wild west of networking. So it is a very simple rule that if you have data, transmit the data as soon as it is ready. So transmit it immediately. If your signal hits another signal, a collision occurs, both packet dies. The devices wait for random time and then they try again. Because anyone can talk at any millisecond, collisions are massive in this. Its maximum theoretical efficiency is tiny as 18.4%, right? And the rest of the time is wasted on data crashes. And if we talk about slotted OHA, Aloha, it is engineers have realized that they needed a bit of structure, right? So they introduce a master clock that divides time into discrete rigid slots. Okay, so we are using the rigid slots, discrete slots. So devices are now told that you cannot just talk whenever you want. You can only start transmitting at the absolute beginning of the time slot. So this simple rule cut the vulnerable collision window directly in half and beautifully doubling the efficiency to 36.8%. Alright, so this was Aloha. Next type of contention based protocol is CSMA-CA, that is carrier sense multiple access with collision avoidance. So this is an undisputed standard for wireless IoT. Instead of trying to clear up a collision after it happens, it works to avoid it. So what we do in this, the devices listen before talking. If it senses a busy channel, it triggers the random back off timer before checking again, preventing the collision from even occurring, right? And now we'll talk about schedule based protocol. Here the competition is completely outlawed. So the central coordinator pre-assign the specific network resource to every device, and this is guaranteeing zero collision, like we talked about TDMA previously. So it is a time division multiple access, as we learned earlier. This cuts the time dimension into slots and each device gets its own turning window. And to optimize this, we have dynamic TDMA as well. So instead of leaving time slot empty, what happens if a sensor has nothing to say, then this DTDMA allocates slot on demand. So for example, if sensor A has massive data log and sensor B is silent, so the system temporarily reassigns sensor B time slot to sensor A. So we are vastly boosting the bandwidth. We are vastly utilizing the bandwidth, right? So this is what dynamic TDMA does. Next type of schedule based protocol is FDMA, which stands for Frequency Division Multiple Access Protocol. So instead of splitting time, FDMA split the radio spectrum. It splits the radio spectrum into separate frequency lane, like turning into data radio stations. So for example, sensor 1 talks exclusively on 2.41 gigahertz, while sensor 2 talks on 2.42 gigahertz. So they talk at the exact same time without interfering with one another. So we are just splitting frequency over here, right? And next type of schedule based protocol is CDMA, which stand for code division multiple access. So this is the most mathematically sophisticated method. Every single device transmit at the exact same time over the exact same frequency band. However, every device encodes its data using a unique code. So what is happening? We are using codes. We are assigning codes to everyone, and they are transmitting the data, and once they reach the location, they are identified using this code, right? So receiver uses the code to separate the different signals from the mixed transmission. So imagine in a room where everyone is talking at the same time. If two people are shouting in English, they collide and jam each other. But if one pair is talking in English and other in Japanese and third in French, your brain can use its linguistic code to tune out the background noise and isolate the language you want to hear. This is exactly how code division multiple access receiver untangles the multiple overlapping digital signals. And finally, engineers realize that contention protocols are great for low traffic that are fast and reliable, but terrible for high traffic. Conversely, schedule protocols are perfect for high traffic but waste slots when traffic is low. So they build hybrid MAC protocol, which is responsible to combine both of the worlds. So there are two types of hybrid MAC protocol. First is ZMAC, which is full formed as Zebra MAC. So think of this as a shape shifting protocol. Under light network traffic, what happens? It switches behavior based on the network traffic. So under light traffic, it behaves as a CSMA. Alright, it acts as a collision avoidance strategy of contention base, letting any node talk instantly for high speed. But the moment network detects heavy congestion and rising collision, ZMAC automatically adapts and enforces the strict TDMA. Alright, structured and collision free. Right, and it instantly eliminates the chaos. And the second kind of hybrid MAC protocol is IEEE 802.15.4. So this is a vital protocol. It is a vital foundational protocol because it forms a physical and MAC foundation to major IoT architecture ZigBee. Alright, it uses highly structured communication window called super frame. So super frame is used. So inside this super frame, it splits the time into two distinct zones. Alright, so there is super frame and the time is separated into two distinct zones, that is CAP and CFP. So in CAP, it is called contention access period, where devices use standard CSMA to send routine updates and competing freely. But in CFP, contention free period, this zone is strictly reserved. So the system assigns dedicated guaranteed time slot here for high priority time critical emergency data, and it gives you raw flexibility for basic tasks paired with guaranteed zero collision real time delivery for emergency. So this is how super frame is divided according to the contention access period and contention free period. So let's advance up the networking stack to layer 3, the network layer. So we are going to look at survey routing protocols. So earlier we were talking about data link layer. Now we'll be talking about the network layer. So once our MAC layer has cleared the path through the airways, routing protocols take over. So what is the job of routing protocols? Their job is to map out the journey for data packet to travel from our source device across multiple immediate nodes until it safely reaches the final destination. Alright, so it is a comprehensive categorization of various algorithms designed to transmit data reliably across the network, particularly in resource constrained environments. Alright, so it defines the rules for how data moves from source device to its destination, often across multiple hops. So there might be many sub destinations in between. So you see, in Internet of Things, we are dealing with LLNs. LLNs stand for low power lossy networks. So these are resource constrained environments where devices have tiny batteries, weak processors, and highly unstable wireless signals. Therefore, an IoT routing protocols have 4 non-negotiable responsibilities. First is energy efficiency. It must find the path that avoid nodes that are critically low on battery so that they don't die in mid-transmission. Then comes scalability. It must gracefully handle anywhere from a few smart home gadgets to over 1 million sensors scattered across an entire smart city grid. And then it also has the responsibility to make sure that if a wind storm knocks out 3 nodes in an open agriculture field, the protocol must instantly detect the failure and dynamically self-heal by calculating an alternate route. Right? Alternate route. And then you have latency management. So it must minimize the delivery delay, which is highly critical for time safety tracking. Alright, now we'll talk about the classification of routing protocols. So the protocols of routing are divided into 3 parts. Right? There are 3 types. So first class is proactive protocols. It is also known as table driven protocols. Alright, so think of a proactive node as meticulously organized traveler who updates a physical map every single morning before leaving the house. So every node in the network maintains permanent live routing table that maps out entire structure of the network. So to keep this table perfectly accurate, the nodes are constantly whispering to their neighbors, exchanging background network topology information at period intervals. I hope you got this point, right? So what are the key protocols which are used in proactive? First is RPL. RPL stands for Routing Protocol for Low Power and Lossy Network, LLNs. So this is a crown jewel, alright, for the IoT network protocol. It is an IPv6 distance vector protocol which is engineered for low power devices, tiny devices. So it creates a destination oriented graph, okay, to route data cleanly up to the central border router. So there is a graph created, a directed acyclic graph. So what it does, it takes the data cleanly to the central router which needs the data. And second, we have OLSR. This is the optimized link state routing. So this protocol uses a clever technique of MPRs, multi-point relays. So instead of allowing every single node to blast updates on every other node, only specific chosen node, okay, for example node A is chosen, only specific chosen node can broadcast the topology update, that how is the map actually laid out, significantly cutting down the clutter which happened in this, right? So because the map are pre-calculated, so the moment the sensor needs to send data, the route is instantly available. So there is zero initial delay. However, the massive drawback is that there is network overhead. So even if the network is completely quiet and no one has data to send, the nodes are still burning up valuable battery, continuously broadcasting that how the table update is, what is the topology, what is the structure of the node, right, the root. So that is the drawback. Then comes to the second kind of approach, that is the exact opposite of proactive, that is reactive protocol, and it is also known as on demand protocol, right? So if a proactive protocol is a traveler who keeps the map updated, the reactive protocol is the traveler who refuses to look at the map until they are lost, right? So they discover the path only when the data needs to be sent. So they are not just aimlessly looking at the map, they just look at the map when they actually need it, right? So when there is a need. Alright, so the sensor node needs to reach a destination, then it broadcasts a route request. So once the path is established, it is maintained until the destination is no longer reachable. Alright, so when a source node suddenly has a packet ready for transmission, it broadcasts route to a route request and the packet out to all the neighbors. So the request cascade through the network until it hits the destination. Alright, so there are key protocols to remember. First is AODV. This stands for Ad Hoc On Demand Distance Vector. So it is a classical on-demand protocol that cycles strictly through an intense route discovery phase when the message triggered it, followed by route maintenance phase to monitor link breaks. Alright. So it performed route discovery and route maintenance. Then come DSR. DSR stands for Dynamic Source Routing. So this uses source routing, which means the sender discover the entire multiple hop path and physically stamp that sequence of instruction directly into the head of every data packet. So the intermediate node doesn't need to check any routing table. They just look at the packet header and pass it to the next name on the same list. So what are the trade-offs? What are the pros and cons? This is incredibly bandwidth and energy efficient. There are zero heavy background updates draining batteries when the system is idle. So then what is the downside? It is initial latency. So when the sensor detects an event, it has to hit pause and wait a few milliseconds to flood the network and discover the path before it can physically send the message. So there is that initial time when it has to wait. So that causes latency in the message delivery. Then comes the third type of approach, which is more of a balanced approach called hybrid protocols. So as you can probably guess, this attempt to combine the immediate readiness of proactive protocol with the low background overhead of reactive protocol. So it is somewhat at the middle of both. So what happened in this? They achieve this by dividing the network into local neighborhoods, or we divide the network into zones. So inside its close local neighborhood zone, the device acts proactively, okay, maintaining tight instant routing tables with its immediate neighbors because it talks to them frequently. However, if it needs to route the message, like for example there is one node and it needs to route the message to a distant node across the network, okay, so across the network, then what happens? It switches to the reactive mode, initiating on demand route discovery only. All right, so there are few protocols in this as well. We'll talk about ZRP, that is zone routing protocol. So this is the gold standard example. So it explicitly establishes a local routing zone framework around every single node, utilizing intra-zone routing, which is proactive inside the parameter, and inter-zone routing, which is reactive, which is applied when we are sending the package globally. So what are the trade-off? If we talk about pros, it provides exceptional optimized balance for massive complex networks like smart unit grids. All right, it delivers lower discovery delays than pure reactive protocols, and it consumes very less power than any kind of protocol. So what is the catch? High operational complexity. Building this device can dynamically switch between distance vector logic. There are multiple algorithms. Then there is some link state logic which is required, which require complex software as well. So it takes away chip memory as well, and it takes a lot of time and efficiency to actually build this kind of protocol network. So to understand routing protocols, think of them as a GPS. Okay, think of them as a GPS of digital world. Their job is to find the best path for data to travel from sensor to a server. Right. So first we have proactive protocol. Let's understand this. So for example, imagine a smart hotel where every room has a smart lock and a thermostat. So since the room never move, right, so the central computer keeps a permanent table for every location. Okay, there is a permanent table for every location, every room's location. And if you want to unlock the room 302, the signal travel instantly because the path is already known. However, the system uses a lot of battery power, constantly checking if every single room is still online, right? So this is what proactive protocol does. And if we talk about reactive protocol, imagine a smart wildlife tracker where sensors are attached to a moving tigers in a forest. So because the tigers are constantly moving, a permanent map is useless. So when a sensor needs to send a tiger location, it shouts who is near me that can reach the gateway. Alright, so this saves the battery because the sensor stays quiet when the tiger is sleeping, but there is a small delay while it finds the path. So that is how reactive on-demand protocol works. Now let's look at a critical phase of setting up a wireless sensor network, which is sensor deployment. You can write the most brilliant routing code and use the most expensive digital sensor, but if you physically place them in a wrong spot, your entire IoT project will fail. So sensor deployment refers to a strategic physical placement of sensor node within a target environment to form the wireless sensor network. Alright, so it is an absolute bedrock of perception layer in IoT. Why? Because the quality, accuracy and truth of the data collected by your network depends entirely on how your nodes are distributed across space. Right? So what are the core aspects to consider during the deployment? So when planning the placement of sensor, several critical factors must be evaluated to ensure that the network functions efficiently. First is the coverage. So this answers the question, can the server see the entire area? So the absolute goal is to eliminate all the blind spots if there is any. Alright, to avoid and eliminate the blind spot so that every point in the target zone falls within the sensing range of at least one node. Then comes the connectivity. Connectivity is coverage doesn't matter if sensor cannot talk to anyone. So node must be close enough to their neighbors or central gateway to establish a stable radio link. Alright, allowing data to hop across the network to the cloud or the sink. Right? Then we have energy efficiency. If you place node too far, their radio wave have to transmit at maximum power, draining their batteries. So strategic geometry minimizes the multiple hop distance data that has to travel, stretching battery life for years. That is why there should be a strategic planning to make sure that there is energy efficiency for our sensors. Then is the environmental constraint. So real life isn't flat cardboard, right? Concrete walls in a warehouse block signals and rough mountain ridges prevent you from placing the node exactly where you want it. So these constraints might be a cause of inefficiency. And then we also have cost. We need to make sure that every sensor is cost efficient, right? So you must balance the absolute budget of the project against the minimum number of nodes required to maintain the performance. So there should be a good balance because every sensor costs money, so it should be used efficiently. So now we'll see various sensor deployment strategies. So what are the kinds of techniques, strategies which we can use for deploying the nodes or deploying the sensor? Right. So we divide the sensor deployment into two parts. So first is the random deployment. Alright. So there is random deployment in which the sensors are dropped, for example, from an aircraft. So it is a kind of strategy in which human access is impossible, so we use random deployment, like flying an airplane over an active volcano or a raging forest fire or a dropping thousands of node out of a cargo bay door, whatever. Alright, and then we have deterministic strategy in which the sensor are placed in a specific pre-calculated patterns. So engineers carefully calculate the exact coordinates for every single node. Alright, so first we'll talk about the random strategy, what random deployment. So these are the types of random deployment. First we have uniform deployment. So sensors are in the broad strategy where sensors are distributed evenly across an area to maintain steady density. So it's best when you are monitoring a massive ecosystem like a vast forest. So you have no idea where a hotspot or an event like a fire will start. So you spread your bets evenly, right? Next we have square grid deployment. This is the most basic pattern. So you place your sensor node precisely at the corner or the vertices of equal sided square. Now let's look at the regular triangular deployment. So if we talk about triangular deployment, here the sensors are splayed at the corner of equilateral triangle. So this pattern is a massive setup in coverage efficiency. Because triangle interlock tightly, their overlapping sensing areas cover 2D plane beautifully, leaving zero gaps. So it actually requires significantly fewer sensors to cover the exact same square footage compared to the square grid, right? So we use this when we are doing precision environmental modeling, where blind spot could ruin the scientific experiment. Next we have hexagonal deployment. So this is where the sensors are arranged in a honeycomb pattern, sitting either at the center or the vertices of regular hexagon. So mathematically the hexagon is single most efficient shape of tiling a 2D plane. So it naturally minimizes the wasteful overlap between neighboring sensors while guaranteeing the absolute gap-free parameter coverage. So this is the gold standard for wide area open field IoT application, such as tracking moisture across massive commercial agriculture farmland. Next we have tri-hexa deployment. So for high stake environment, we use tri-hexa deployment. So this is a highly advanced hybrid pattern where you take a hexagonal framework and nest equilateral triangle directly inside it, right? So this create a massive degree of connectivity because the nodes are tightly interwoven. Every single node has multiple immediate neighbor within radio range, right? So what is the real world impact? This pattern provides maximum reliability. If a military drone strike a section of network or a critical industrial asset experiences an explosion, then that destroys several nodes, right? So the remaining sensors can easily bypass the dead zone using alternative routing loops. So it is strictly reserved for critical industrial infrastructure or military combat surveillance, where system downtime is not an option. Other type of deployment strategy is deterministic sensor deployment strategy, and it is used in various applications such as environmental monitoring, structure health monitoring, and precision agriculture as well. So it is used to ensure that the sensors are placed at an optimal location and they provide accurate and reliable data while minimizing the cost and energy efficiency. So there are two types of deterministic sensor deployment. First is grid-based deployment. As we discussed, this is simple plug and play layout where sensors are separated by a fixed rigid distance. So it's easy for an installation technician to execute, but because it doesn't care about environmental conditions, it can lead to massive node redundancy and poor energy optimization. Whereas we have Voronoi diagram deployment. So this is a sophisticated algorithm approach. So a computer model takes a target space and mathematically slices it into different geometrical regions called cells based on the proximity to specific point. So each sensor node reacts as a generator or heart of its own Voronoi cell. So you look at this is the random deployment. This is how square grid sensor deployment works. This is the triangular, this is hexagon, and this is the tri-hexagon deployment. And if we talk about grid based, this is how it looks like, and this is the deployment of Voronoi sensor strategy. Now, as we dive deeper into the communication mechanism of Unit 3, we need to talk about how data actually move through the network plumbing. So, two fundamental traffic handling processes that you must master are data aggregation and data dissemination. So, let's break down. So, the first one is data aggregation. So imagine you have 10 temperature sensor deployed inside a small server rack. So if it's a stable day, right, all the 10 sensors might continuously report the exact same data point, say for 24 degrees Celsius. Every single second they'll report the same data point. But every sensor blindly sends its own independent packet across the wireless medium all the way to the distant cloud server. So what happens? The airways get heavily congested. The network queues back up, and the tiny batteries on those the sensor drain within weeks due to constant radio transmission. Right? So data aggregation is an engineering solution to this data flood. So if same data set is coming from multiple different sensors, you need to aggregate the data and provide only one data set, right? So it is the process of collecting raw data from multiple IoT sensors locally, filtering out the useless noise or duplicate entries, and combining them into a single clean condensed dataset before shipping it to the upstream. Alright, I hope you understood this concept. Now let's flip the network upside down and talk about data dissemination. So while aggregation is all about moving the data up the chain, compressing many inputs into one cloud summary, dissemination is about moving data down or across the chain. So it is the strategic process of distributing or broadcasting critical information, system alerts, or direct operational command from centralized source or like a cloud platform or an edge gateway down to the thousands of specific nodes, actuators, and users. So dissemination rely on robust routing protocols and messaging patterns to ensure that when a system decision is made, the command safely and efficiently hits the correct physical target without getting lost in a transit. So let's understand the difference between the both. First of all, data aggregation is a many to one pipeline. So it takes thousands of raw data stream from edge of physical world, refine them into a single data funnel, right, and send it towards the cloud database. Whereas on the other hand, data dissemination is one to many or few to many pattern. Okay, so it is branching out one single point of authority to vast array of target actuators. If we talk about the primary goal, it is to reduce the data volume and eliminate redundancy and to save the energy and the bandwidth. Whereas data dissemination primary goal is to distribute the critical information, updates, and control the commands to specific nodes, right? And if we talk about the data alteration, so in data aggregation we modify the data, but in data dissemination we preserve the data. We deliver the message exactly as intended without any altering in its content, right? And if we talk about typical triggers, so aggregation is generally routine and time driven, such as a sensor checking every 10 minutes on a steady cycle, whereas dissemination is a fundamentally event driven. That means reacting instantly to a threshold breaches or human override command or sudden system alerts. So together these two workflow form the complete circulatory system of any modern IoT application, seamlessly managing both data collection and the real world physical response. Now let's look directly at the hardware anatomy of the world's most popular IoT prototyping board, that is Arduino UNO. So to write an efficient code for the perception layer, you must understand the physical board layout, right? So let's have an overview of how these components actually work. Alright, so first we'll talk about the hardware components. So first comes the ATmega 328 microcontroller. So this is a large block of silicon chip, okay, and it is undisputedly main brain of the entire board. This is where your compiled code is physically stored inside the flash memory and executed line by line. So this microcontroller controls everything else on the board. Then we have USB port. So this serves as a dual phase. Okay, we have USB port. This serves as a dual phase. First, it acts as a data pipeline to upload your compiled code from your computer IDE into microcontroller brain, and second, it draws a steady 5 volt of electrical power directly from your computer to run the board during desktop prototyping. Then we have power button, right? So all we can also known as power input. So when you deploy your completed IoT project into a field like smart irrigation system, you can't leave it plugged into your laptop, right? So there is a barrel jack or power input that allows you to power the board independently using an external power supply. Then we have voltage regulator. So this is an external power source. You can fluctuate dangerously. So if a battery surges and send 12 volt directly into the delicate 80 mega chip, right? So you will instantly fry the silicon. So the voltage regulator act as a shield. Okay. So voltage regulator, it act as a shield from what? From dropping and smoothing out incoming voltage to be safe. Alright, then we have crystal oscillator. So computers don't have a concept of time unless something ticks. So this tiny silver component you see over here, crystal oscillator, this tiny silver component is the metronome of the board. It ticks exactly 16 million times a second, right? Every tick coordinates a clock cycle inside the microcontroller, allowing your code to execute timed events with microsecond precision. And then we have the reset button. This is the reset button. This is your physical panic button. Pressing it doesn't erase your code. It simply cuts off the execution momentarily, flushes the temporary memory, and starts the board and focuses your program to run from the absolute beginning of your script, right? And then there are status indicators. So for status indicator, while troubleshooting the hardware, the board speaks to you through these status indicators. First we have power LED indicator. So this is a small onboard light, right? So you see where is power LED? I'm unable to locate. Okay, so power LED, right? So this is onboard light that is wired directly to your power rails. So the moment the board receives electricity, whether from it is from USB port or from the barrel jack or from the power button, right, the light turns on. So if you plug your board in and this light stays dark, you know instantly that you have dead power source or a short circuit, right? And then we have TX and RX LEDs. All right, we have TX and RX LEDs. TX stand for transmit and RX stand for receive. So these light indicate active serial communication. So when you're uploading a fresh program from your computer or when your Arduino is actively streaming sensor data back to the terminal, these two LEDs will blink furiously, proving that data packets are moving over the wire, right? And then we have pins and headers. All right. So these pins are touch points where your code interacts with external hardware. They are strictly divided into functional zones. So first we have digital input output pins. So from pin 0 to 13, you see we have these pins. From 0 to 13, these pins handle binary data, meaning they only understand two states, either high is 5 volt, and either low, 0, right? So you use them as outputs to flip an LED on and off, or as input to read whether a physical push button is present, right? Alright, and then we also have analog input pins. So analog input pins you see over here from A0 to A5, right? So these are the real world IoT sensors like gas, temperature, or light, whatever sensors they are put into these. So they send continuous varying voltages. So these 6 specialized pins channel the signal into the controller. All right, it sends it into the microcontroller. Internal microcontroller's internal ADC. ADC stands for analog to digital converter, and turning a smooth voltage curve into a digitalized number between 0 to 1023. All right, and then we have AREF pin. So this stands for analog reference. So if you are reading a highly sensitive sensor that maxes out an exactly 3.3 volt instead of 5, so you can supply 3.3 into this pin. So this recalibrates the ADC stop resolution scale, making your sensor reading much more precise. And after the pins and headers, we have power and ground pins. So it comes as WIN. So WIN stands for if you don't want to use the barrel jack but still want to power the Arduino from external battery pack, so you can wire the positive lead directly into this pin. Then we also have GND. GND stands for ground. So electricity cannot flow unless it has complete path back to the source. So the ground pins are the return path. Every sensor and actuator you connect to the Arduino must share a common connection with those ground pins to complete the circuit. Alright. You see over here we have ground pins, right? So this is where you need to actually come. Then we have 5V and 3.3V pins. So these act as a power sources for your external peripherals. If you connect it directly, right, to a digital temperature sensor, you can run a wire from these pins to feed it stable, regulate the power directly from the Arduino's onboard supply. Then we also have a reset pin, just like the physical push button we discussed. Grounding this pin with a wire instantly reset the microcontroller. So this helps you to build an external trigger circuit or safety trip wires that reboot the machine automatically. And lastly, we have ICSP pin. So this is a 6-pin cluster stand in circuit serial programming. So what it does, it bypasses the USB port entirely, allowing advanced developer to attach a hardware programmer directly to the ATmega328 chip. So this is used to flash low-level code like boards, bootloader or program chip in mass production. Now that we completely understand how this hardware stack is put together on a single board, we need to understand its place in the bigger picture. In the Internet of Things, data doesn't just sit statically on a single device. It undergoes the continuous cyclic journey. So the data is captured right here on these analog and digital pins, right? So it is captured over here and it undergoes it is compressed inside the microcontroller, right, inside the ATmega328 processing brain, and transmitted via network protocols across the wireless medium and handled via data aggregation and data dissemination pipelines until it transforms from raw physical stimulus into meaningful real world action. So remember this hardware foundation, because every line of networking code we study is designed to control these exact copper traces and silicon gates. So what is an emulator? An emulator is a powerful software tool that completely stimulates the real-time physical behavior of Arduino hardware. right? So why is virtual prototyping an absolute game changer for engineering students? Because it is hardware free testing. You can learn, write code and connect wires virtually without spending money on the physical development boards, on jumper wires, on sensors, right? And there is absolute operational safety. So in real life, if you miswire a circuit, like connecting a raw power rail straight to the ground pin without a resistor, you will cause a short circuit and instantly fry your microcontroller chip. So in web based emulator, nothing happens except an error log, right? So it provides a safe environment. Then it is cost effective. It unlocks free access to massive inventory of expensive components like complex graphic display, Wi-Fi shields, etc. And it provides debugging and quality control. So an emulator gives you a control environment where you can slow down execution, step through your code line by line and find technical gaps or logic bugs before deploying your project into the physical device. Alright, so there are few popular web-based tools like Walkwe and Tinkercad, which are the industry standards. So you simply drag and drop a virtual Arduino and create your own connection via virtual wires to LED or sensor, and write your code in C++, right, and hit the play to see if you can run exactly as it would on your physical desk. Like we already have an overview of Arduino, that it is an open source electronics platform based on flexible and easy to use hardware and software. So there is a board which we have in detail discussed about all the hardware components, and then there is the ecosystem, Arduino ecosystem. So remember, Arduino is an open source platform and it uses easy to use hardware and software. And in context of IoT perception layer, its primary job is to simplify complex electronic interfacing. So instead of writing low-level assembly code to change raw registry bits to a microprocessor, Arduino gives us a clean interface to map out our sensors and actuators completely. And if we talk about Arduino integrated development environment, what is this? This is a cross-platform software application which is written in Java. So what happens is, first you write, compile and upload the code to the board. So when you do this, there is a compiler present inside the IDE. So this internal compiler, what it does, when you write the code, it is human readable text. So the compiler translates that text into binary machine code, a stream of zeros and one, to the microcontroller that it can execute, right? So the interface also include text editor, right? It also include toolbar for quick actions like verify and upload, and incredibly important serial monitor as well. So this serial monitor, it acts as a text terminal window, allowing your physical board to send data strings back to the USB cable to your laptop screen so you can debug your code in real time. So guys, if you don't want to reinvent the wheel of IoT by writing thousands of lines of raw timing diagrams protocol, we import the libraries. So what are libraries? They are collection of pre-written code that add advanced modular capabilities to your sketches, right? So just have a look at these four kind of libraries which are mostly imported in your IoT data code, right? So first is the communication libraries. These include wire.h, which allows your board to coordinate data with multiple chips, right, on an I2C data bus using just two wires. And then we have SPI.h. It handles high speed serial peripheral interface communication for quick data devices. Then we have hardware control libraries, for example servo.h. So this simplifies the motor control, so you can rotate a robotic arm to a precise angle with a single clean line of code. right? And we also have liquid crystal.h. So this library translates simple text string to pixel control lines on a character LCD display. So when you are actually diving deeper into IoT, you will be able to understand which library is used when, right? So right now let's just have an overview of the major libraries which are used in our IoT code while writing it with the Arduino. Then we also have IoT and networking libraries. So these are vital for our course, right? For example, Wi-Fi.h or Ethernet.h. What they do, they allow your board to join the local network and to access the global internet. And once it is connected, then we have pub sub client.h, which implement the lightweight MQTT protocol, which lets your sensor node publish telemetry data package straight to the cloud brokers. And lastly, we have sensor libraries like dht.s, right? So this library is specifically designed to handle the complex timing communication protocol used to pull clean, calibrated temperature and humidity readings from sensor like DHT11 or DHT22. Congratulations guys, you have just completed the heavily conceptual and highly technical unit of this IoT, which means it is an absolute gold mine for you scoring easily top marks in your exam if you revise efficiently. So do not try to blindly memorize the paragraphs of the text. Try making keyword matrices, visualize the geometry and follow a data flow. So please ensure that you tidy up your lectures tonight while these concepts are fresh in your mind. So review your notes, try Padhai Logic, review the videos again and again, create structural frameworks, and you are ready to crack your exam. So thank you for your incredible energy and focus. Get to the work. All the best guys for your exam, and I'll see you all ready to dominate Unit 4 in our next lecture.